Hello everyone, I hope you all are doing good. Till now we have discussed about the nucleation and growth. All the theories we have, most of the basic theories we have discussed, and sometime before in one of the earlier classes we said that we will be discussing about TTT diagram. So after learning all these things, nucleation and then the phase diagrams and the generation of phase diagrams, today or not today, in the next few series of lectures we will be discussing about TTT diagram, TTT diagram is time temperature transformation diagram, and then we will be discussing about CCT diagram, so continuous cooling transformation diagram. And then if you want to understand these diagrams, it is very important to know about the phase diagrams. So we will be discussing about two types of phase diagrams, eutectic and then iron cementite phase diagrams. So how the different types of phases evolved with the temperature or the variation in temperature and composition. These things we will be discussing in detail as much as possible in say the next 3 lectures or maybe 2. We will see how many lectures we need for that. So anyway, suppose you have a material. So if you have a material, or suppose you want to make a material for some mechanical component or some structural application. So if you want to make a material for some structural application, you will be looking for some very basic properties like say strength. Until and unless your material is strong, you won't be able to use it for any structural application. And then the second most important property is the say toughness, or say you can say also ductility, and the chemical stability. So these are the very basic properties that you would be looking for in any material that is required for any structural application or to be used for any structural application. Now strength, when you say strength can be defined by yield strength or tensile strength or say any other strength that you may define for your depending on the design criteria. Now the toughness is nothing but the area under the stress strain curve. This is the energy that a material this is the energy that one material absorbs before it fractures. This is also important. And ductility, if your material is ductile, you can give it different shape, you can deform it. So this is also an important property. Now chemical stability, say chemical stability we can think of say it should not react and dissociate or degrade the mechanical property. Say for example oxidation is one, and say corrosion is another one example. So in these cases the material, if it corrodes a lot, you won't be able to use it for any structural application, because after some time it will degrade or disintegrate from the structure. So these are the very important properties. Now these properties, these are the very basic properties. Of course for a very specific application you may need some very specific properties in the material. Say for nuclear application you would be looking for irradiation, good irradiation properties of material, and there are many other very specific properties. Now these properties or say mainly say the strength, which is a very important or the very basic requirement for any structural material. So these properties depends on generally these properties depend on some factors. So what are those factors? So one would be say constituent elements, say iron, carbon, chromium, manganese, silicon, etc. So depending on the constituent elements, the type of bonding will be varying, and accordingly you will get different types of accordingly you will get the different strength or other properties. The constituent elements and also composition say weight percentage of weight percentage of the elements, these also matters. Say for an iron carbon alloy, if you vary the composition, you get a wide varieties of steel or cast iron. So accordingly their strength also varies depending on the percentage of carbon that the alloy has. And apart from that, the crystal structure or say phase structure and morphology of the so crystal structure and morphology, phase structure, all these things also influence a lot. Material with different morphologies having the same percentage of say alloying element gives you different level of say strength or say ductility or say the chemical stability. So that is why this morphologies and the crystal structure is also very important. You will see that when we will discuss say 0.8% carbon steel, say eutectoid steel, the morphology of say perlite and bainite is different, and there the strength also varies. So the phase morphology influence or the crystal structure influence a lot the mechanical or say chemical properties. And apart from that, the prior history of loading also matters. Suppose you have a material, if the material is already cold worked, then there will be large number of defects, or say the defects can be dislocations, vacancies, etc. So or twin boundaries, so prior history will change their concentration, defects concentration, and accordingly the strength will be varied depending on the prior history of loading. And also what matters is the concentration of say precipitates. If you see aluminum alloy, generally say 7075, the second phase the precipitates are generally very hard, and then they also resist the movement of dislocations in the material, and then plastic deformation becomes very difficult. So your strength goes very high. You can have some precipitates which are very bad also for mechanical properties, or say some chemical properties, say oxidation, or say for corrosion. Sometimes say chromium carbide precipitates in some stainless steel at certain range of temperature is very harmful for intergranular corrosion. So precipitation also influence the properties. So anyway, we know that we need some basic properties in the material, and these properties are influenced by this different factors. Now once you have a material, the alloying element will be fixed, their composition will be, overall composition will be fixed. But now if you want to alter the mechanical or chemical properties of the material, you can do different types of heat treatment, and for doing the heat treatment you need to have a very good knowledge of time temperature transformation diagram, CCT diagram, and then the phase diagram. So that is why we have discussed this thing, so that you understand the importance of studying this. Of course this whatever we will be discussing is mostly for iron carbon alloy, which is the most widely used materials that we see in our everyday life, and we will also discuss about some eutectic alloys. So but however eutectic kind of transformation you can see in iron carbon phase diagram also. So this is the background that you should remember. Now say TTT diagram, whatever we wrote here, the properties, most of this can be changed by doing the heat treatment. Overall composition of a material may remain same, but the local composition you can vary by doing heat treatment, that we will see. So in the precipitation also you can change. Say if you take any other example, the phase structure you can change, the crystal structure you can change. So there is a great possibility of changing the mechanical properties quite a lot just by doing the heat treatment. Heat treatment means you are not melting the material, you are below the melting point, you are heating the material, and with some particular design of cooling, say at different schedule of cooling, different cooling rates for different intervals, cooling and holding at different rates, you get the different types of crystal structure, microstructure, and you change the local composition, and then you get the different types of mechanical properties. There these two diagrams are very useful. So if you see the TTT diagram is time, temperature, transformation diagram. It is also known as isothermal transformation diagram, say IT diagram. So this diagram, why it is called isothermal? Because this diagram, if you remember, when we get this kind of TTT diagram from the nucleation rate diagram, where we get the nucleation rate for a given undercooling. So the temperature remains same. So that means the transformation takes place at a particular constant temperature. So that's why it is called isothermal. But in most of the cases in industrial say applications, if your workpiece is very wide, so very thick, say railway wheel, if you are making it, you need to do some heat treatment. So it is a very thick specimen, you cannot very precisely control the temperature constant throughout the thickness. So there it becomes very difficult to control the structure or the say to predict the structure based on the TTT diagram. Of course it is useful, but there when the temperature is not constant throughout the structure, or say in industry it is not only about the structure. What happens generally in industry, you don't do the heat treatment at constant temperature, or say the transformation at constant temperature is never happens in industry. Most of the cases in research you can definitely do. So in industry what happens, the cooling rate varies. So or the transformation is not isothermal. In industry it is most of the cases continuous cooling. Say in case of very thick or wide specimen, the temperature across the the dimension will not be uniform. Outer side maybe the temperature is less, if you go inside maybe it is high. So you can have a temperature variation. So isothermal transformation is never possible, because while cooling it is very difficult to control temperature, to control uniform temperature and to achieve a isothermal transformation. So generally in that cases the CCT diagram is very useful, because the cooling is continuous, it is not isothermal. So CCT is continuous, or say continuously cooled transformation also, say continuous cooling transformation. So it is cooling is continuous. And these two diagrams are not very different, that we will be discussing. So now we will be discussing about TTT diagrams. So we will be discussing about TTT diagram. So as I said earlier, it is isothermal, thermal transformation, diagram. So equilibrium is achieved during the transformation. So you can say it is a reversible process actually. So reversible isothermal process. So anyway, if you want to understand the TTT diagram, suppose here I just draw a part of the phase diagram, iron carbon phase diagram. So this is temperature and this is say weight percentage of carbon. So you have the alpha ferrite region, and then you have this gamma austenite, then alpha plus gamma. Here you have gamma plus Fe3C, and here you have perlite. So this percentage is 0.8% carbon, here it is 0.02%. So in the end it will be 6.67% carbon. So we are not drawing this part, this is only a part of the phase diagram. So suppose you have a material, the moment you have a material, the composition is fixed. So the composition is fixed. Here it is 0.8% carbon, eutectoid still. So this is called eutectoid. This temperature is called eutectoid temperature. So this temperature is around 723 degree or 727 in some book, degrees centigrade. Here it is 910 degree centigrade. So on this line you have pure iron Fe, and then you see the carbon percentage increases, and then you get different types of phases. So once you have a particular material, the composition is fixed, and if you see the thermodynamic state variables are composition, pressure and temperature. So pressure is also fixed here, because this is done at at a particular constant pressure. So now the temperature is the, you see, if these are given for a particular material for transformation, moreover the pressure has got very minimum effect on condensed phases, say solid or liquid. So pressure, we need not worry much about pressure. Composition is fixed for a given material. Now this is the temperature, which is the only variable we have to control the microstructure or the phase structure. So this is why in TTT diagram generally the temperature is changed in a way that you get different types of phases. So I am here just drawing. In earlier classes we have seen that temperature versus time. So this is in degree centigrade. So earlier classes we have explained that TTT diagram, actually if this is the, say we call this is the temperature, say here as we are considering gamma to perlite transformation, we are considering gamma to perlite. Perlite is what? Alpha plus Fe3C. So this is, if you come here, it is touching the alpha boundary, and on that side it will be touching the Fe3C boundary. Here you have Fe3C. So this is, perlite is a lamellar structure of alpha ferrite and cementite. So as we said that this time temperature transformation diagram is nothing but the reciprocal of nucleation rate I versus T diagram. So this diagram is, TTT diagram is reciprocal of x axis is reversed actually. Then we get the TTT diagram. So here the temperature would be, say we call it, this temperature 723 would be T capital E, eutectoid, T capital E, eutectoid temperature. Now above this eutectoid temperature you have everything gamma, you have stable gamma phase. Now what happens, this figure here shows you that the starting time for nucleation. So starting time for nucleation of what? It depends what will be nucleated, it will depends on the type of material, that means the composition. Say for example here we are considering 0.8% carbon steel, or say eutectoid. So this is, here we are considering, say this is for eutectoid steel. So for example this is, say, for 0.8% carbon steel, say eutectoid steel. Suppose you have a austenite at this temperature. Now if you bring down the temperature and give it sufficient time, hold it at this temperature so that your transformation is isothermal. Now what will happen, after this amount of time the nucleation of perlite will start. You will have perlite, but there will be some gamma also. Once you give it a sufficient time, what will happen, you keep on holding this this material at this temperature. With time the percentage of perlite will increase, gamma will be, more and more gamma will be converted to perlite, and then after this amount of time you will have all perlite in this side. So this is what. So now what happens, if Suppose if you come down this way, you know come down to this nose and then you hold it like this, then also what will happen, the austenite at high temperature, now this is your this amount of your undercooling is this much, this is your undercooling delta T. Delta T is T eutectoid minus, say this is the transformation temperature. So this temperature, what will happen, after this amount of time, gamma will be transformed into whatever phase. So here it is called, and below this nose it is called not parallel but binite plus gamma. And once your transformation is completed, at this time, this is called, and this line is called finishing or finish line or time actually. Once you allow this much of time, all the gamma will be transformed into binite, and you will get binite here. So P is perlite, B is binite. So perlite and binite are actually having the same composition, only the difference is in the morphology of the phases. That we will be discussing what kind of morphology you get in case of perlite and what kind of morphology you get in case of binite. So now binite, if your undercooling is just here, so just below the nose, you will get coarse binite. If your undercooling is very high, you will come far below this nose, your undercooling will be very high, so as a result you will get very fine binite. So below this nose you get binite, above this nose you get perlite. And perlite also you get, here you get coarse perlite, here you get fine perlite, but above the nose, just near the nose you get very fine perlite, because undercooling is increasing. If you come here, hold it here, your perlite transformation will start here and then it will end here. Here you will get all perlite, but it is fine. Here it is coarse. Suppose you cool the austenite phase. Suppose you are here in this region, so it will not start any nucleation. Like the austenite is still austenite, but it is called metastable austenite. So in this region also it is metastable. So metastable and unstable are two different things you have to remember. Unstable means it will quickly be transformed into a stable state, but metastable means here generally or to be very specific, metastable means you need to give some activation energy. It is locally stable actually, until and unless you give it sufficient time or give it some activation energy, it cannot transform. So for here, why do you need the time? Because time is necessary for the diffusion to occur, diffusion in the movement of atoms to start the nucleation. So that is why you need to give some time. So, and then what happens after, suppose if you cool it very fast, you don't cross any of this or you don't hold it here, after certain temperature what will happen, you will get, if you cool your material very fast like this, so you don't intersect with the any part of this starting time or nucleation time, time required for starting the nucleation. What will happen, the austenite will be transformed into martensite. So this is called martensite start MS, and after some time whole austenite will be transformed into martensite. So this is called martensite finish, this is called martensite start. So these are the different terms that you have to remember. So let us redraw this diagram and then explain the thing clearly, what we learned from. So this is, you take by temperature TE, this is temperature degrees centigrade, and this is time. See here, suppose this is martensitic start MS, this is M finish. So this temperature is this temperature, this is also known as A1 temperature. This temperature is known as ACM, cementite nucleation temperature, and this is known as A3. A3 means this is the boundary between gamma and alpha plus gamma. So below this temperature alpha phase will nucleate in the gamma phase. So we get a curve like this. So here it is almost parallel. Why it is parallel here? You see, if you, let us explain this. This is the starting and this is the, so this is the finishing. So this is just like schematic representation, you should understand. It is not very perfect here in my drawing. So what happens, you have austenite above this temperature. Here you have austenite metastable, above this you have, here you have gamma plus perlite, here you have gamma plus bainite, and you have everything here is perlite above this line, but it is coarse, here it is perlite fine, here it is bainite, it is called upper bainite or say coarse, here it is called lower bainite, lower, or it is fine bainite. So and this is, here you have martensite. Martensite you will have also in this region, you will have some gamma also. Here it will be all martensite, because this is the finishing line. Before the martensitic transformation is completed, all the gamma is completed to martensite, there will be some gamma also. Now if you see this curve, as your temperature is very close to T temperature, T, what will happen? Delta T is very less or tends to 0. So that means the driving force delta GV, delta TH, delta H by Tm. So this is proportional to delta T. So the driving force for nucleation is very less. Nucleation is very less, the nucleation will take long time. So that is why you see it is almost impossible here. If it is almost close to the, say you take to temperature, perlite will not be transformed. You need some undercooling to start the nucleation. As your undercooling increases, here the driving force also increases. So your nucleation time decreases. This curve varies with percentage of alloying elements, say, or the percentage of carbon in iron carbon alloy. This moves to left or right depending on the amount of carbon. Now as your undercooling increases, the driving force increases and nucleation rate becomes faster, so you need less time for nucleation to begin, as well as you need less time for completion. Now if your undercooling is below this nose, So your undercooling is so high and your transformation temperature is so low. What happens? Then the diffusion, say diffusion is d0 into xp minus delta g d by kT. So if your temperature decreases, diffusion will also decrease, or say flux is minus d dc dx. So these are the, so how the flux of atoms, that means the movement of the atoms, number of atoms that can diffuse through per unit area, it also decreases. So as a result, what will happen? Diffusion becomes very difficult in this region. As you go down, it will become more and more difficult, and you would require more time for nucleation. So as your undercooling becomes very high, then there will be some diffusion, but diffusion in this here will be very short range diffusion. Atom will not be able to diffuse a lot, they will diffuse by very small distance. So actually, so atom will diffuse to a smaller distance, and then you get a very fine structure. So you can see as you go down, the fineness increases, the morphology also changes, and hardness increases. In this direction, hardness increases. Say here it is around 5 Rc, then say in this case you get around, say fine perlite you can get 30-40 Rc, something like this. Upper bainite you can get around say 50 or something. Here you can get around say 55 or 60 Rc, say 60 Rc, but here martensite you can get here actually say 55 Rc, local hardness. Martensite you can get the maximum hardness. Here in martensite, in case of martensite, you see undercooling is so high, and you are not intersecting this any the nose or any part of this nucleation starting line. So what will happen? Your cooling rate is very fast. So when your cooling rate is very fast, it is not, diffusion is not possible here. So for stainless steel, the martensitic start transformation temperature is around 200 degree, 200 little bit more than 200 degrees centigrade. So at this temperature you are coming from say 700 to 200 degrees, in this time is around 1 second. It is 1 second. This is generally plotted in log scale. This axis time is plotted in log scale. For 0.8% still it is around 1 second. So what happened? Your cooling rate is so fast and undercooling is so high. Temperature is so low that diffusion becomes impossible. So it is actually diffusion less transformation, martensitic transformation. There what happened? The crystal structure changes, arsenic crystal structure changes to martensite by shear deformation. The FCC crystal structure becomes martensite, which is BCT, body centered tetragonal. What is this? This is nothing like the say BCC structure. In BCC structure, what we have? In BCC we have say lattice parameter A equal to B equal to C, and all the angles are alpha, beta, gamma are 90 degree. But here in BCT, A equal to B but not equal to C, angle remains the same. So it is little bit distorted structure. BCT is little bit distorted structure of BCC, but notice that from FCC we are getting BCC, but there is no diffusion, there is only some changes in the lattice parameters, so permanent change. So this is why, that is why it is called shear transformation, shear deformation assisted transformation. Here above this it is diffusion assisted transformation. In this case it is activation, it is the driving force which decides the time. In this region, this is the diffusion which controls the time. So these things you should understand. Now this is what we have explained based on the theory that we know for nucleation. How will you get this kind of TTT diagram experimentally? To get some such TTT diagram experimentally, what you need to do, suppose you take a material and then you heat it to this temperature, somewhere above this. If it is say 0.8%, temperature has to be above 723. If you are at room temperature, generally it will not be austenite. So if you have a paralytic still, ejected still, you have to heat it above 723. You have to superheat, because for perlite to transform into austenite you need to give superheating also, like we do supercooling in the case of austenite to paralytic transformation. For paralytic to austenite you have to go for superheating. So your temperature has to be above 723 degree also, plus the superheating that is required, that we have discussed earlier. Now what will happen? You have austenite, so you are here, say Samir here. Now what will happen? If you keep the material and then suppose you have a bath, say temperature is say T1 is say somewhere here, T1. So you take out your material from the furnace and put it in this bath where the temperature is maintained at T1, and hold it for, generally molten salt is used. Generally molten salt is used, or people used to use this kind of approach earlier. Once you have this specimen here, you hold it for different amount of time, say hold it here up to this amount of time, and then you quench it, take it out and put it into another water bath, that will then it will be quenched. So once you quench it, you can just this is for just for explanation only, you can do it in the different types of furnaces also. Nowadays you have very sophisticated furnaces. You have a material at austenitic temperature, you cool it to a particular temperature, hold it for different amount of times, and then you quench it. Say here, from here you quench, from here you quench, from here you quench. So like this you go on doing this quenching experiment like this. So what will happen? You will realize that the austenite, the material, you have different austenite grains. Until you come here, everything will be austenite only. There will be no transformation. Once you cross this line, then you will see some perlite formation. Perlite formation. This will be something like this. So these are like different plates of ferrite and cementite. So ferrite and cementite, the space between is called alpha ferrite, and the black lines are called Fe3C cementite. So similarly, in all directions, in all the grains you will have perlite. So from this side also it can grow like this. So and here also it can grow Generally, the parlitic growth will be normal to the grain boundaries. So once, suppose you come here, you hold it for this much of time and you quench it. So what will happen? Here you have everything austenite unstable. You have started forming perlite, but when you quench it, the remaining austenite which was there earlier, then it will become martensite, and the martensite will have a different kind of structure. Martensite will have something like this. So we will discuss what is martensite, but once you hold it for this much of time, then inside your structure, say everything will be perlite. So this perlite is called, this is Fe3C, and in between you have alpha. So these are parallel lamellar plates of cementite and ferrite, cementite and ferrite. So this kind of alternating arrangement of cementite and alpha ferrite is known as perlite. Here what you get, so 100% perlite. So that is how you see, if you cool it, hold it for different amount of time and quench it, and you do the microstructural analysis, here you will see after this much of time, you will see perlite in the structure. Then after this much of time, you will see everything is perlite, and then if you go here, everything is perlite, then you quench it, you will not get any martensite, because perlite cannot be transformed into martensite. Austenite can be transformed into martensite, because austenite is FCC phase, single phase. If you want to transform it into a martensite, only you need to deform little bit by sharing the structure, little bit rearrangements will be there in the atomic position. So but here the perlite is a mixture of alpha plus Fe3C. So these two are very different crystal structures. This is orthorhombic and this is alpha is say BCC structure. These two cannot be, without diffusion it is not possible to get a single phase perlite out of these two phases, sorry, martensite out of these two phases. It is very difficult to get martensite from this alpha and Fe3C. So after this amount of time, you will see no changes there. By this, now if you do for another temperature, say T2, if you continue like this, you will get start time and finishing time. So this is at one temperature, this is say another temperature, start time and finishing time. You increase the undercooling, you get another start time and finishing time. You come here again, hold it. So now if you connect this finishing point and start point, you get the TTT diagram. So this is how, actually nowadays you don't need to quench it all the time. There are different instruments. Dilatometer is one such, which continuously can not only dilatometer, there are various instruments nowadays which can constantly monitor the fraction of say perlite or any kind of phase changes, and it can very precisely give you in one test you can get the start as well as the finishing time. So this is also possible. Now you see, suppose if I increase the time, this is the say this is the starting time at temperature say T1. Temperature, if I bring it down here is the starting time and say here is the finishing time. Now if I draw the fraction of say perlite, this is the volume fraction of perlite. The volume fraction of perlite will change like this. This is called Abrahamic kinetics. It is given by some equation 1 minus F equal to 1 minus K T to the power n. T and n are constant, sorry, K and n are constant, T is time. So this is a kind of S curve which gives, so with time what happened, the volume fraction of perlite increases, but initially it increases, then it remains almost constant for certain amount of time, then it decreases. Once you increase the time, it will not change anymore. So if this is say for T1, for T2 it will be shifted like this. So at the nose it will be here, and after that time, after this you come to the nose point, so this temperature say T3, so this is T3, say T2, then again it will go to move to the right side. So from this equation you get the volume fraction. So if you know the start time from nucleation theory, you know the growth, the kinetic, this equation, it gives you the finishing time. So you can get the analytically also you can get the start and finishing time, or based on the Abrahamic equation.